All right, here we go. We're going through the Physics 201 formula sheet for exam 4. Okay? And we're going to tear this thing up. First off, this is for sound. Velocity is frequency times wavelength. Now, with sound, velocity is usually 343. That's not always true. If we're talking about a wave on a string, this is the velocity of a wave on a string. So these two being close together is kind of a good thing. Because if it's a string, you're going to have to find the velocity with this equation, then use this. Okay? This is the generic wave equation. Rarely on a test, but it has been there once or twice. The form of this is really, really weird. To me, I'm used to this form over here. Okay? 1 over t is equal to the frequency, so this is really just frequency, and over here you have wavelength. I'm used to this format. This format's weird, and I haven't really seen much of that format. Okay, this one right here is a standing wave on a string, and a pipe open at both ends. So this is standing wave on a string, a pipe open at both ends. This one over here is a pipe open at one end. And this is both ends. Okay? So this gives the frequency of the sound produced by a pipe open at one end, frequency of sound produced by a pipe open at both ends. Okay? Now moving onwards, here, this is all intensity right here. This is intensity of sound. This equation down here is the surface area of a sphere, because sound usually radiates out in the direction of a sphere. And this is the power output. This is the same thing. It's intensity only in decibels. I naught is usually 10 to the negative 12th. Okay? So this ends up just being a ratio of the actual sound intensity over the threshold of human hearing. And I naught's not given on here. This is beat frequency, just a subtraction of two frequencies. This here is weird version of Doppler. But it's missing the proper sounds, the signs. It should be V plus or minus VO over V minus plus VS. And I don't know why he didn't put the signs in there. That's not proper. So the top half up here is all sound. Everything up here is sound. Now we're getting into the non-sound down here. This is all thermal, starting down this way. So we're getting into thermal physics. We have our temperature conversions all the way across the top. These are temp conversions. Okay. Yeah, that equation I haven't seen in a while. These are thermal expansion. This one's not. This is thermal stress. Not something I see on a Ford test very often. In fact, I've never seen on a Ford test. But these two are thermal expansion. This is linear expansion. That's volume expansion. Okay? These two are heat capacities. Okay? Calorimetry, ice cubes melting, that sort of thing. That's when you use these. This is heat transfer. How does heat get from one object to another? You have radiation here, and you have conduction here. Okay? Now moving down here, we're starting to get to thermodynamics, which is the meat and potatoes of this test, I hate to say. Okay? And this gets to be fun down here. Avogadro's number, but some of you haven't seen that in a while. Total mass is the number of moles times the molar mass. PV equals nRT. So we got pervert right here, and here's the value of R, 8.314. That density? That looks like that's density, which is weird to me. Here we've got the kinetic theory of gas. The kinetic energy is equal to 3/2 nRT. Same thing here. Average kinetic energy is 1/2 mv squared equals 3/2 kT. This is for one molecule. This is in general. Okay, and we got the naked pervert, where it's the ideal gas law in terms of Avogadro's number. That's what this really is. Okay, here you got number of moles, here you got number of molecules. So the big N here is the number of molecules. Okay, And again, this is also the kinetic theory of gases. It's just solving for velocity. It's using this equation here and solving for velocity. Here is the second law of thermodynamics, which is fun. And we get into the real thermodynamics down here now. Here, work equals pressure times change in volume. Here we have another work. This is isothermal. Here, delta U equals Q minus W. Again, thermodynamics. This is the second law. I was wrong. This is the second law. Not this one. Okay. Constant. This is, now this goes back up to Q, the MCAT. Where are you? Way up here. Q equals MC delta T. Now this works for liquids and solids. It doesn't work for gases. So when we get to gases, we have to start using these equations crossed here. So this is working with specific heat of ideal gases. The specific heat of constant pressure is the specific heat of constant volume plus 8.314. Here, gamma right here, and of course he doesn't have gamma on here. Oh, he does. Gamma's over here. It's CP over CV. And it comes out to be a ratio. It's like 3/2 or something. I'm not sure the ratio off the top of my head. But if you go through and solve this, it comes out to a ratio. And this is an ideal, the version of the ideal gas. This has to be a monatomic ideal gas. Same thing here. Okay. Now we get down in here, we're still dealing with thermodynamics a little bit, but we're starting to move into heat engines. Okay. This one's a Carnot heat engine. It's an ideal heat engine. This one over here is just a regular old heat engine. Okay. And if it's Carnot, we can rewrite the efficiency this way. This is just saying work. This is part of the heat engine equation. It's saying work is the change in the heat from the high reservoir to the low. This is a coefficient of performance. This is more for heat pumps. Okay, and here's entropy. He does put these equations on a test, a coefficient of performance for a heat pump. All right, that's a quick run through this sheet. The bottom half is where you're going to sit on most of these equations on most of the tests, unfortunately. Okay, and you do need to know what all of these are right in here because he picks on these. And there's a couple he picks on down here with the adiabatic expansion and things like this that aren't really here. So make sure you memorize some of the thermal equations for finding work with adiabatic, isothermal, isobaric, isochloric, because a lot of this isn't here. Okay, so make sure you know how to find work with all the different types of thermal processes. There's a quick run through that equation sheet. Have a good one.